Welcome to the video series on integration and differential equations. In this first video, we're going to look at the power form. The integral of u to the n with respect to u is equal to u to the n plus 1 over n plus 1 plus a constant. So more intuitively, to integrate some power of u, we're going to be increasing that power by 1, we'll be dividing by that new power, and we'll be adding on a constant. And since that's our key formula, I'm going to put a box around this. Technically, there's a restriction on n. N can be any real number not equal to -1. We'll explore the case where n is equal to -1 in a later video. Why don't we try some quick examples here just to get warmed up. So first quick example, if we wanted to integrate u to the 4th power with respect to u, we'd increase the power, it's now u to the 5th, divide by that new power, and add on a constant. Let's say we wanted to integrate u to the -7 with respect to u. We're going to increase the power. If it's a negative power, it'll become less negative, so it's u to the -6 now, and we want to divide by -6. So let's make that -1/6 times u to the -6, and we'll add on a constant. Final quick example, let's say we wanted to integrate u to the 3/4 with respect to u. We're going to increase the power. If we add 1 to 3/4, we're going to get 7/4. So our new power, 7/4. And then we'd like to divide by that new power. Well, to divide by a fraction, that's the same thing as flipping that fraction and multiplying. So 4/7 times u to the 7/4 plus c would be our answer. With that, we're ready to move on to some typical examples. So here's our first typical example. Let's evaluate the integral of root cos x times sine x with respect to x. The idea is that we're going to do a substitution here to make this look like our key formula. Here's a tip: when working with the power form, we let u equal the quantity that's raised to a power. So when we look up here at our integral, we see that the cos x is sitting under the square root, so we can think of that square root as being a power, and if we follow this tip, then we would let u equal the quantity that's being raised to that power. So in other words, u would be cos x. To continue with our substitution, we'll need to calculate du. So we'll take the differential of u by taking the derivative of cos x. That's going to give us minus sine x. And to turn that into a differential, we need to multiply by dx. So there we've got our du. So now we need to ask ourselves, what else is sitting in this integral? We've already taken care of this root cos x, but the other stuff that we've got to deal with here is the sine x dx. So I'm going to copy that down. Sine x dx, I'm going to put a circle around this, and I'm going to say this is coming from our integral. So we want to be able to rewrite this expression in terms of u. So it's all about the previous step. We know that du is equal to negative sine x dx. What we want, positive sine x dx. So to move from this step to the next one, we're going to have to multiply by -1. So we could say negative du is going to be the same thing as sine x dx. So really two things going on there. You're looking at what have we got in the integral that we want to re-express, that's our sine x dx, and then we're asking ourselves, how do we get from the du step to the next step? How do we need to transform du? In this case, multiplying by -1 was what we needed to do. So often I put a box around this part here. Now that that's done, we can go back to the integral in the question, and we can say the integral is equal to the following integral. So the root cos x, we're going to rewrite that as root u. And the other stuff that we've got in the integral is our sine x dx. We've figured out that we can rewrite that as negative du. So I'm going to put the du at the back. Any constants can go out in, or any coefficients can go out in front of the integral there. So I'll say negative integral root u du is what we've got. So let's continue our calculation over here. In order to continue this calculation, it might be helpful to rewrite that root u as u to the 1/2. And now we've clearly got an instance of the power rule. We've got u to the 1/2. We know how to integrate that with respect to u. So we would get negative. I'll just leave the negative out in front here. Integrating the u to the 1/2, we're going to bump up the power. It's going to become u to the 3/2. We're going to divide by that new power, so that's like multiplying by the reciprocal. And we're going to add plus c. And then finally, we want to get our answer back in terms of our original variable. So we're going to replace that u with a cos x. So two ways to leave our final answer. We could say it's minus 2/3 cos x all raised to the power 3/2 plus c. Or there's a shorthand notation that we could use when working with trig functions. We could put the power right on the cosine and say that's minus 2/3 cos to the 3/2 x plus c. So I'd just like to point out an example of something that we can't integrate. We can't integrate square root of cos x with respect to x. It does not look like the power form. The reason is when we go through our substitution, if we go through these steps that we did in this first example here, we would not have been able to find the du. So our du came out to negative sine x dx. We'd look back at our integral and we'd say, where's this du going to come from? So this integral of root cos x dx does not fit the pattern of the power form. Let's try a second typical example. We're going to evaluate the integral from 0 to pi over 2 of root cos x sine x dx. So this time we've got a definite integral. We can see the 0 and the pi over 2 on the integral. Those are our limits of integration. So let's run through a similar thought process as we had in our first example. Typically we let u represent any quantity that's being raised to a power. So we'd let u equal cos x. And then we'd figure out our du. So we'd take the derivative to get negative sine x, and to turn that into a differential, we'll say negative sine x dx. Okay, then we look back up at our integral, we figure out what we've accounted for. Yep, we're going to be able to rewrite that root cos x, but it's the sine x dx that we're now going to be looking for. So we'd ask, how do we get from this step to that step? Well, what we'd be doing is multiplying by -1, or alternatively, you could say divide by -1. Either way, it's the same thing. So doing that same operation on the left side, negative du is another way of rewriting sine x dx. Now, in this problem here, there's going to be an additional step because we're going to have to deal with the limits of integration. So let's think about what happens when x is 0. When x is 0, which is our bottom limit of integration, what would that mean for u? Well, u would be cos 0, which is 1. If we do the same thing for the top limit, when x is pi over 2, u would be cos pi over 2, and that's equal to 0. So the idea is that these new numbers, the 1 and the 0, those are going to get put on the integral when we go through our substitution. So let's rewrite the integral in the question. Just continuing our work over here, we can say the original integral is equal to the following. The limits are now 1 and 0. So let's be a little careful about that. We're used to often seeing a bigger number on the top limit of integration, but it's not always the case. the way that we know for sure is that we need to replace that x equals 0, which is the bottom limit, replace that with a 1. So that 1 really is becoming the bottom limit of the integration. Okay, so integrating from 1 to 0, and what we're integrating is root u, and we've decided that sine x dx can be written as negative du. So I'll put the coefficient in front, and I'll put the du at the back here. So same kind of integration process as we had in our previous example. Let's be clear that 1 is the lower limit, 0 is the upper limit here. So there we go. Let's rewrite that root u as u to the 1/2, and then that'll make our integration go a little bit more smoothly here. So I'll keep the negative out in front. Integrating the u to the 1/2, we're going to get u to the 3/2 times 2/3. And if this were an indefinite integral, then we'd be writing plus c. But this is a definite integral. We've got numbers that are going to be plugged in here. So we'll put 0 on the top, 1 on the bottom, no plus c required for this definite integral. All right, so let's plug in. We've got minus 2/3 times, evaluating at 0. Well, 0 to the 3/2 is going to be 0. And then we'll subtract off what we get at 1. 1 to the 3/2 is going to be 1. All right, so overall, we've got negative 2/3 times negative 1 would be positive 2/3. And that's our answer. So I want to just briefly compare what we did in our last two examples. So in the first typical example, we had an indefinite integral. We had no limits of integration in the problem. And so our answer came out in the form of a function plus c. So remember that with an indefinite integral, when you get your answer, what that answer represents is the set of all antiderivatives of the function that you started with. So this function here, that's the set of all antiderivatives of root cos x times sine x. C in this context represents any constant, any real number, since no matter what value this c takes on, this function here is still going to be an antiderivative of root cos x sine x. So in our second typical example, we looked at a definite integral, and the answer came out to a numerical value. It was 2/3. That value represents area under the curve. So if we were to sketch from 0 to pi over 2, and if we were to sketch the function that we were integrating, so that was y equals root cos x times sine x, let's just indicate some scale here. Let's say that's the y value 1. Just very roughly, this function is going to look like this. Something like that. And what our definite integral is telling us is that if we calculate the area under the curve, so we're looking at the function that we're integrating, we're looking at the area under that function from 0 to pi over 2, we're saying that area is going to be 2/3. So that's the conceptual difference between the indefinite integral and the definite integral.